Welcome everybody. So as usual, you get a little bit more details in my talks, so I will also show some code slides and so on, So actually, it should be a lot of fun because the Lucene committers also have a lot of fun in the recent years, especially with the introduction of native access, because that's now easy possible with later Java versions, and I will talk about that. And there are also some ongoing projects which might come in the future, but did not yet land on the main branch, and that's a nice overview. So my background is, as I was introduced already, I'm a PMZ member of Apache Lucene and Solar, and I'm also working with Elasticsearch and OpenSearch, sometimes opening bugs and so on. Actually, my main work is at the University of Bremen, Marum, where I'm doing a long-term archive of scientific data. That's the reason why you have the numeric search in Lucene, because that was my background somehow, how I came to the Lucene project, and for consulting I'm also available. So actually this is now something like a repetition of what Adrian, just arriving here already, said shortly before. Only the numbers are a little bit different because it always depends on when you start counting. So we have already almost more than 25 years of Lucene. It depends when you start counting, because it's actually at the moment 24 years at the Apache Software Foundation when it started as a project. And now the next slide is also a little bit about the current community. So we have at the moment 69 PMZ members and 103 committers. That was the status report of the Apache board. And in the second quarter of 2025, we had a lot of issues and pull requests. And you see the ratio between open and closed pull requests is quite nice. And what's also very, very nice is, unfortunately, Lucene at some point split the repository with Solar, so we lost a lot of forks because of that. But the old repository, which was together with Solar, had 2.7K forks, but the new one has a lot more. Yeah, that's about the Lucene evolution. So I'm just repeating what Adrian said before. So Lucene 1.0 was around the 2000s. Then we got Lucene. Really some major steps in Lucene was in Lucene 3.1. We started to merge Lucene and Solar together into one project. This was 2011, 2012. Lucene 4 came out. This was a major rewrite of lots of parts of Lucene. So we had codecs, four-dimensional posting, stock values, FSA, FSTs. Then Lucene 6, we got numerical and point queries. So that was the second stage of what I already implemented a lot earlier in the 2.0 Lucene versions. And then a little bit later, we got the blockmax run in Lucene Solar 8. And now we are coming close. So in 2021, we released Lucene 9.0, which was also a major step. One of that was moving to Lucene 11. So this forced a lot of code changes. So everything was adapted to the module system of Java, and therefore a lot of packages was renamed. So there was a lot of things to do for the developers. So I think the Elasticsearch main branch was not only 100 errors, but it was it was an upper limit, something like thousands of errors. But and at that point it was also a split of Lucene and Solar again. As we heard that Lucene 10 was released last year, Solar is still on the 9, and hopefully it will release Solar 10 also soon. And that was basically the part where the HNSW vector search was introduced, which brings me a little bit now to the latest stuff, which is coming now in Lucene 10. Where we changed a major part. So we changed a lot to Java 21. This goes forward, and in Java 21 we have some opportunities to directly access native memory. Also, the memory map directory was rewritten to get rid of all those 32-bit byte buffers and everything. And we have now native calls which we can make use of. And this started around Lucene 10. We had some backports to Lucene 9 at that time, but it was only more for testing purposes, because we have some sophisticated way also to run code which is developed for Java 19, 20, 21, although in the Lucene 9, which is on Java 11. And that's the challenges that we have. So first, I'm coming to what actually drives us to everything beyond Java 21, which is, of course, modern, but it's not the last step. And this is mainly everything around the project Panama, because it allows to do really partly native access and also access memory off heap from the Java virtual machine. It allows to include third-party libraries. I will come back to that a little bit later. But also we can better interact, for example, with the operating system kernel through the libc library. And that's everything that's coming. So Project Panama is basically described as improving and enriching the connections between the Java virtual machine and well-defined but foreign non-Java APIs, including many interfaces commonly used by C programmers. That's the official text on the Project Panama page. Project Panama started around Java 13, 12, 13. I don't exactly remember when it was started, but it was for a very, very long time until it get almost production ready. So the key concepts of Panama is, the first thing is it's everything around something which is called memory segment and var handles for access to memory somewhere outside of the Java heap. That's basically how you could describe it. The good thing in contrast to byte buffers is it's using longs for addressing and not integers, which somehow limits us to some crazy limits around 1 gigabyte, not 2 gigabytes, because of the -1 problem. And so because the integers are signed, of course. So actually, that's one of the problems with the byte buffer, which also have you seen, and some other stuff like that the unmapping of byte buffers didn't work. So that's all solved there. And there's also a second part, which is the Panama foreign, which is function support. So it allows to natively call a method in some C library or Rust library or whatever, everything that follows some C calling conventions directly from Java code. Actually, you don't need a stub or wrapper in Z code like you did it for CNI or with all those other, and it's also fast. So actually, a call with Panama method handles is approximately the same if the code is optimized like you're doing a virtual call in a C object. So basically there's no overhead, which makes it completely different, especially for some loops like where you call those methods, those functions, those external functions quite often, because you don't have the calling overhead, which is there if you're doing the old style JNI, which is available since Java 1.0 and applied by several libraries. So basically, this is something which is really new. The first one, the Panama foreign, was already used in Lucene 9, which is Java 11, but with some tricks I will show you in a moment. It's also working there. And the Panama foreign function support was added recently in the Lucene 10 versions, and we are still moving forward. The last one, which is also very, very interesting of the project Panama, which is a vector API, which I showed you 2 years ago in another talk, where we have improved the calculation of the vector products that you need to measure the distance in the HNSW index and also to execute those queries. So we got speed improvements of 4 times in contrast to the original Java code by that. So Panama Vector API is also available, but it has some problems still there today. So it's really very, very bad to use at the moment. So this is why we are still focusing on going ahead with the Java versions now. So the problem is, so we have here seen a lot of features, and the cool thing is, and I said Java 21 is available, which is a long-term release, and we would like, and we based our newest version 10.0 based on that Java 21 version. So all looks fine because except the Panama vectors, this part here, the Panama foreign, is already available in the main APIs of Java 21, so you can readily use it almost, because unfortunately there are some problems, and I will show you with that. So Lucene 10 targets Java 21, so Lucene 9 Java, was 11. So the problem now is that Panama foreign has some special state in the JDK in the Java 21 version. I was doing my best to get it out of that state for the LTS release, but unfortunately it got this stupid preview flag. So the API is almost stable already, so you can use it, and it's also forward compatible. At least there were some minor changes for the 22 version of Java, but it's only really minor things. So theoretically it would work in later versions, but unfortunately if you compile your code against that, the class loader says no. And why does it happen? Because there is something, so we have that preview. What happens is the compiler makes class files which were compiled against preview APIs, and the class loader does not allow you to load them. So if you want to run a Lucene application, you would have needed to enable the preview mode, but this would lead to the fact that we could not remove the old byte buffer-based API from the Lucene 10 version, because it would be an opt-in feature. And that was the biggest problem. And if you don't pass enable preview, the class loader says, no, I cannot load that class. And how that happens is, if you look at those classes, unfortunately this is Java 19, because that was a screenshot, there's something strange. There's a minor version of 65535, which is -1 as a short, as a minor version of the class file. So actually what happens is, if you compile any class with Java C, and the output class file is marked as Java version 19 in that case, which is 63, but unfortunately it's marked with that minor version -1 in a short as being using any preview APIs. And because of that, the class loader says, no, I cannot load that, unless you have set the preview flag. And the second condition is you have to run on exactly that version which is given there. So that means the Lucene, if they have that preview flag, would only run on Java 21, only with the preview flag, and not on 22. So we cannot release that. And this limitation is really the big showstopper that was following us. And we had that already in the previous version, so we had some ideas how to fix that. So the first thing is, does anybody know what the easiest way to fix that would be? Yeah, sure, you can simply remove that -1 there by hacking the bytecode, which is what we did at the beginning when we were testing with Java 19, where the preview flags in memory map directory was already there. In reality, you'll see some Gradle code which just jumps to the byte in the class files and removed that flag. And I think Elasticsearch is still doing that at some places for the later versions. So basically, this is also a workaround. But the problem is, with the vector API, this does not easily work, because the vector API changes all the time. So you need to be correct, compile against the correct version, and you need to compile against each version of the Java API. And therefore, we needed some other way how to do that. So we did some tricks here. I will not go closely to it, but the compilation trick is very, very old. It's basically similar to what the JDK is internally also doing when you are passing the release flag. When you're passing the release flag to the Java compiler, actually, it does not compile against the latest version of the Java API. It has some extra zip file somewhere in the JDK where it has some signatures of the old class files of the previous versions with some differences. So actually, when you say -- release 21 on 24, it uses the class library of 21, which is somehow in a compressed way inside there. So basically what we are doing here is we are emulating exactly the same in Lucene. So whenever a new Java release comes out, for the APIs, like the Panama APIs, we're doing some extraction, so to not fall into some problems with of course, intellectual property. We try to avoid, so we are only preserving the signature of the methods. So actually what we are doing is, in Java 21, we are extracting the APIs, we remove all the bytecode from those classes, it's stored in the Git repository, and then during compilation, we are just compiling against class files which do not contain any bytecode anymore, just the method signatures of everything that's public. So basically, that's what happens in our case. We have an JDK 21 API char in the previous version of Lucene 9. We also had one for 19, 20, and 21, because there was major changes between them. And then we had a separate compilation archive here, Java 21, where we are compiling with some special tricks to do that. So here's just some code for those. So actually the trick is we have some jar file, we patch that into the base module of the Java compiler, and we also export the JDK incubator module, and then we are creating something which is called an EMMA jar. So we have class files for different Java versions in the jar file, and the class loader selects the correct version that is needed. Actually, with Java 21, it's not as bad anymore as it was before, because actually we only have that Panama foreign in the preview version of 21, and the vector API, luckily it didn't change in later versions, so 23, 24, 22 all had the same vector API because it's somehow stuck. So it's in the incubator, so we didn't need to regenerate those, so at the moment we only have that single 21 one. And actually, it does not create an EMMA char out of it because we are compiling for Java 21. It just merges that additional class files in the separate compilation unit into the main class file. So it just mixes them together. There's a little bit of logic in that Gradle there. So basically, we compile against the stub, and then we are testing it with different Java versions on the Jenkins server. You might know we could also use the toolkit API, but the problem was, if you're using the toolkit, this still does not work because it adds a preview flag, so we have to remove it again. That's the other problem. So this is better because we are also removing the preview flag in those stub Java files, so we just compile against normal Java classes without a preview flag. And the second problem is, if you would like to compile Lucene-relevant, it would download 3 or 4 versions of JDKs just to compile that shit, and some Lucene committers were complaining against that for security reasons or whatever. So we decided to go that route. So if you have any project that does something similar, it might be a little bit interesting to you to do that. So actually, it's like the same like with the boot class path that you have seen long ago in early Java versions. We are just putting our own class files to replace what's already there in the JDK. So basically, that's what's happening with some tricks. And what we get out is a Java file, Java class file, and a jar which works, is compiled against Java 21. Also, it might also only work at a later version, but that's basically how we do it. So we don't use any reflection like a normal project would do it, because reflection would be too slow for that, because we're calling that stuff very often, and it needs to be completely optimized by the compiler. So we really need to really compile against that stuff. So that's basically what we're doing. And what is now implemented with the Panama foreign on our side? So first of all, we have the memory map directory. As I told before, we're using memory segments to map the whole index files into virtual memory, and we leave it up to the Linux kernel or the Windows kernel or the Mac OS kernel to page in our index and treat it like it would be local memory in RAM. So basically, think of the Lucene index like a big swap file, and the Linux kernel just swaps in the pages which it currently needs to execute the query. So we don't need to have anything to do with the loading or adding a buffer pool or something like that, because the kernel leads us. Some people might now tell us, yeah, there was a paper 2 years ago which says never ever do that with a database because it breaks you. Yes, with a real database where you need ACID, it breaks, and it also has some slowness problems at some points, but this got recently better in recent Linux kernels. So actually all those things like it's only limited to one thread or whatever is no longer really applying because it changes. So there are some good things with the newer Linux kernels, but there are also some bad things. I'm coming back a little bit later. So actually, use memory map directory, of course, with your index, because there it is, the whole index is treated like memory. So we can execute our queries directly on it. We can also doing our vector multiplications directly with the vectors stored somewhere in the file. We are just giving the Panama vector API just a memory segment and say, multiply that memory segment with another memory segment. And then it just executes the vectorized code, and we get the result. So basically, that's done. There's only one limitation. At the moment, there is no mentioning of the memory segment in any public API of Lucene, because you remember on Java 21, it's still preview, so we can't do that. And therefore, to do some interaction between the components in the codecs, like if you want to multiply a vector, there is some hidden interface on the index input which marks it as memory segment, so only the 21 code sees it, and the other codec can then reuse that code to hook into those methods. This was invented by Chris Haggerty, which did a lot of work on that. So basically, behind the scenes, it communicates on the side of the official public APIs to do some optimization at some points. So this makes it hard to maintain at some points, but that's unfortunately the problem with the preview bullshit. That, yeah, some people call it really bullshit, because it's more rigorous than the incubation feature, because it has that limitation that the class loader says no. And because of that, it's really, really hard to maintain. So the second thing is that you also want to see, so we have now memory outside of our heap space, and all the index is loaded into memory automatically by the Linux kernel. But one problem we had for a very, very long time is how to tell the kernel which parts of those index do we really need at that time. Or, for example, if you're using vectors, there's a completely different access pattern than if you're just reading stored fields one after another. So actually, the Linux kernel has some internal logic to do that. So, for example, it starts to preload any pages if you're accessing some memory. But sometimes this is not always a good idea to have that automatic preloading. But on the other hand, for example, if you're merging segments together, it would be good to already preload most of the index files, so you don't have the overhead of always falling into those page faults that instruct the kernel to do the swapping from the swap file or index file into real memory. And we want to control that. Unfortunately, Java does not provide an API for that, but the memory map directory now uses the other features of the Panama foreign, which is POSIX madvise. So it can advise the kernel how the memory is used. And so, for example, during merging, and then can tell that we read sequentially, or for example, the vector codecs can do random madvise, and that's available on Linux and macOS. So this is the official C configuration. So it tells you the POSIX madvise function allows an application to advise the system about its expected patterns of usage of memory in the address range starting at address for the size. Basically, that's all we can do, and we want to put that into our code. So when we have the memory segment of the whole index mapped into virtual memory to tell it from byte XY to byte something else, we want to use the normal advice that we have done all the time, or we want to read it sequentially, or we can also tell it that we soon need something, because, for example, if we are reading stored fields, we know that we may need read other blocks afterwards, so we can directly tell the kernel that some stuff at a later stage will be needed, so it can already preload the stuff for us, so when we access it, we don't get any page faults. So we want to implement that, and basically Windows would also have some features like that to be available, but we left out Windows for that case because it's too seldomly used. The Windows people should use the standard normal access for now. But on Linux and macOS, so actually the interesting thing is on Linux and macOS, it's exactly the same signature in the libc. Also, it's not glibc, it's another library. And also the constants behind those POSIX here are the same integer numbers, because you see here it's an integer as an advice. So actually, it's portable between Mac and Linux. So basically, how does it work? The implementation is quite simple using the new APIs in Java, starting with 21. So basically, you just need something like a linker, a native linker. It's easy to get. And then you get a symbol lookup, which is, in our case, because the madvise function is in the libc, we just need a linker for the libc library, the standard POSIX library. And this is behind the default lookup. And then we can just look up our function here. It looks like reflection somehow, so we just give it as a Java int. We have here also value layout address, so we know the second part of that. Here, for example, is an address, and then we have a size and an advice, so we are just mapping that. And then, after that, this returns a method handle, which, you know, it's really something which is a method call in Java that can be completely optimized. And this is where the speed is coming from, so it does not have any real overhead. So here this find function is some boilerplate code, but actually we are looking up here the name of that function. If it doesn't exist, we throw an exception, and then our code says, okay, I'm not running on macOS, it's Windows, so forget about that. And then the native access is disabled. But basically, we get back a memory segment with a pointer. Memory segment can also be single pointer with 0 length. Do that, and then we get a don't call handle with a function pointer that we have. And then, as a return, we get this method handle that we can then simply call later here. Can do a madvise invoke except. We give our memory segment. We give the byte size of our memory segment and the advice, and by that, we can simply tell the kernel for the memory map directory to do that. The other stuff is just boilerplate, because, you know, in C world, you always get return codes, and the return codes need to be interpreted, so it does not throw automatically exception. This exception here is just a bullshit, because a method call on a native method never throws an exception. It's just because the checked exception problem in Java. So you have to somehow put that try-catch around that, which is horrible stupid, but you need that. So actually the error handling is done here, and then we can call that method here from the memory map directory to tell that we want to have a segment which would be a slice, for example, from some bytes in the large memory segment, and tell it, here, this one will be read in random access soon, and that's how it works at some point. So basically, the ongoing work at the moment is we are doing some checks about how to implement it, where to use it. We are also reinvestigating at the moment about random and normal in recent links, because unfortunately with recent Linux kernel 6 point something, there's a new feature which is multi-gen LRU is enabled, and this is enabled, for example, in the latest Ubuntu 24.04 version, for example. And if you have that enabled, unfortunately, for the random access, it thinks if you access it random, I can also throw it away quite soon. And this leads to the fact that the pages which are randomly accessed are freed up from the disk space, not only when there's memory pressure, but also earlier. And this leads to the fact that we got a lot of more swapping on those kernels. And therefore, for example, Elasticsearch had some workarounds for that to be able to disable it. So we are still investigating what we actually should do here. So we are changing our I/O context to use some hints, so the memory map directory can, based on the hardware, decide what in reality should be done, depending on what the index segment is doing. So how about NeoFS directory? Yes, we could do the same with fadvise there. The problem is only we don't have, with the standard Java APIs, we don't have access to the file handle, you know, that integer you need in C code. And because we have no access to it, we cannot really use it. There's a JDK issue open about that, so we can also use it for NeoFS directory, but there's no real updates yet. It's already 1 or 1.5 years old. The alternative would be to re-implement the whole NeoFS directory in native code, but that's nobody we want to do, because you have to rewrite all the writes, reads, everything. You would need to do that in C code, and that we don't want to do just to get the stupid file handle. There's already a Java I/O file descriptor, but it does not have a getter to get that stupid handle behind, which is just an integer. So it's not even a security concern, because everybody knows file handle 1 is standard out. Yeah, so actually, this is something, unfortunately, I was not on FOSDEM this year to talk to Mark Reinhold and tell him we need that feature. Yeah, so actually, at the moment, you only get native access with memory map directory because it's easier for us. So another thing which I will do quite quickly is, there's another thing which is also ongoing. So for GPUs, we also want to use native access, because there's a library provided by NVIDIA, and there was last year a talk about that. And they have now a Java library. At the beginning, it was done using JNI. That was a state last year. But in the meantime, they updated it to also use Panama foreign. And at the moment, we are thinking how to include that. There's an open pull request. So they contacted me and a few other committers last year on the Berlin Buzzwords conference. And basically, the architecture for Lucene would be, we would have an additional codec, and the codec would call those Java implementation, which then uses the Panama API to talk to the native library. The problem why it was not yet merged is, the problem is, you need always a pair, so the vectors written to this cannot be read by the normal Lucene codec and vice versa. So actually, you need to use a codec in that case. So on all your searcher nodes, you also need a GPU to execute the queries. It would be nice to only do that during indexing, but unfortunately it doesn't work because it's a proprietary format, how the HNSW index is represented in the GPU, and therefore we are somehow writing some black unknown code, unknown data file in the index, and this is one of the problems. So the Elasticsearch people are working on that to figure out what we can doing, but at the moment this is a little bit stuck. So the last one is quite fast. I have some 5 minutes or It's okay, yeah. So last one is so Lucene 9. The dev model in Lucene 9 was we had a branch main. We were preparing for the next release in an additional stable branch 9.x. So we had Lucene main branch, was already on Java 17, I think. At the end, it was Java 17, and was as a last stop updated to Java 21, but the branch 9x was on Java 11, and many PRs and changes of the main branch were cherry-picked to the branch 9x. So in Lucene 10, basically, it's the same. So Adrian talked about that already. So we will have here a main branch for the future Lucene 11. But here we did a little bit of change now. So during the preparation, we are now updating the Java version as soon as possible when a new Java version comes out. So the stable branch is on Java 21, but the new main branch is already on Java 24 at the moment, and we are just waiting for Java 24 to update it. The challenges with that is, of course, we have a more diverse, more changes in the main branch, incompatible changes because language version updates and so on. So backports got harder. So this would also lead to more often releases. But the other problem is also that there's, unfortunately, when Java 24 came out, we had to wait a few weeks because Eclipse toolkit was not ready to do 24. And also Gradle is unfortunately very, very slow on updating Groovy and its dependency to ASM internally. So this is really horrible. So it took us 4 weeks and after the release to update that, just because all the downstream projects that are somehow used by our build system are not yet updated to the new versions. But actually what we want to do is to stay on the last version. And another challenge, of course, is that we somehow need to align our major Lucene releases, as Adrian talked before. We changed that already, also to the Java LTS versions, because if we would release now Lucene 11 with Java 24, everybody would complain, oh, this is out of support in 2 months, or I think it's already out of support somehow. Because it's a version. So actually, the earliest time we can now release Java Lucene 11 is when the next LTS version comes out in September, which is Java 25. And the other challenge is, of course, removal of security manager and access controller, which is other headaches I don't want to talk about now. But this is something where we have to figure out. So actually, what you will figure out is that Lucene 11 will come out after Java 25 came out. Of course, it will not be directly afterwards, but with a small delay, hopefully. And I hope we have enough major features. I think there's already a plan, like you told, for October. I don't remember. October this year. Somebody told it on the mailing list. I don't know. Yeah, but don't expect anything about that. So basically, but it would also fit the 2-year cycle of Java would also fit the recent developments in Lucene. So if we could align, it would make life easier, but we can always have a little bit of delay. But unfortunately, there's a little bit of linking between those versions, unfortunately, if we want to go to the latest Java versions from now on, which we already did. So just as a last slide, there are already some brand new from the Java 24 branch. So at least we, not the Groovy people, did not do that now, but we already removed ASM, which is always outdated when a new bytecode version comes out. We removed it already from the main branch, so the expressions module using the internal APIs of Java and also that API chart generation that I've shown you for the compilation is also changed to the new code. So that was everything, and I think the food is already waiting for you. So we have 2 more minutes for one question, or I don't know.
Yeah, thank you, Uwe.
Yeah.
Any questions? Questions?
Yeah. I can't tell you when Lucene 11 comes out.
You already told. September.
Yeah.
So just maybe first a layman question about Java memory management.
Yeah.
Why do you want to use off-heap memory? Is it just for optimization?
And no, actually, that was in earlier talks. So actually, if you read that blog post here, you can understand why it is like that. So basically, because we don't use memory outside of the heap, the idea is to use virtual memory. So actually, what we are doing is instead of loading the whole index file into heap space, we just tell the kernel, here's the index file, make memory out of it. Virtual memory, and then we can access it. That's basically what you want to do, because this spares you additional copying between heap space and memory. If you would do your code only on heap, you would need to first copy it from the file system cache to the heap, and this is an additional overhead. And you also need to do a syscall. But on the other hand, with memory mapping, you have a page fault. So and other limitations. But yeah. That's basically.
Thank you. And just if I can, a second quick question, another layman question on Java. You talked about Panama Foreign and native code. Does it break Java code portability?
Of course, yes. You need of course, you need your own checks to figure out, like we did, we are throwing an exception there and then disabling that. So we have something like a provider interface. So we have a native POSIX provider interface, which gives us the native methods for that madvise. And if it's on Windows, it just falls back to do nothing in that case. So because it's an advice only and an madvise, if we just comment it out on platforms where it doesn't work, that's fine. So basically, yes, that's a problem. But this is always the case with native code. So,
thank you.
But actually, the memory map directory is not a problem. Only those native code calling. So memory map directory is fully supported internally by the JVM.
Another question? No. I was wondering about the problem, the limitation that you describe using the enable preview. Is it something that the Java maintainers want to change, update, or fix, or leave it like that, or what?
If Chris Haggerty would be here, he has closer contact to them, so he's also not really happy about that. So basically, I think it was a bad idea to do that, but I think nobody wants to change. If there's a YEP and the YEP was already said this goes into effect, then they won't move away from that anymore. That's unfortunately how the OpenJDK development works. Once a feature is released, it will be not modified anymore, only extended. So you cannot go back for backwards compatibility reasons. So that's basically the problem. There's only those workarounds. There are some reasons behind that why you want to do that, because if the API is not stable, you want to make sure that the class can be accidentally be loaded in a newer JVM where it would lead to some linkage errors. But on the other hand, we have that under our control somehow by checking the Java versions. So we are safe to remove the preview flag. It's a hack, but yeah. Unfortunately, this is something. So other projects are doing similar stuff. So actually also modifying the class files with random access file, changing some bits is done, I think, in Elasticsearch. As far as I remember, there's a plugin for Gradle doing that to remove the preview flag. Yeah, that's unfortunately, it's not nice. So vector incubator is much easier to do. Also, it's called incubator. It's much easier to handle. Yeah, it's strange.
Thank you. Let's thank our speaker again.
Yeah.